This is Macy here, and we're going to go through pedigrees and specifically how you can identify different inheritance patterns by looking at these. Okay, I'm going to start off with some basics. When you look at a pedigree, it's a series of circles and squares that are either colored in or not. So I'm going to give you just a review of what these symbols mean. Okay, if you see a square, that means a male, and if you see a circle, that means a female. Now, if the circle is colored in, then that means that that individual is affected. If the shape is not colored in, then that means that the individual does not express that trait. Now, when you see a line connecting individuals with a line that goes down with other individuals, that symbolizes two people that had children. Now, in order to determine what kind of inheritance pattern is shown in a pedigree, the only way to do this is through the process of elimination. You can't really prove that something is a certain inheritance pattern, but you can prove that it's not other types of inheritance patterns. Two of the easiest things to start with are Y-linked traits and mitochondrial inheritance. That's because those are two very obvious ones that you can really easily cross off the list of options. Okay, for example, if there is a trait that is carried on the Y chromosome, then only men and males can express that trait. Okay, that's because males have an XY chromosome, whereas females have an XX chromosome. So if females don't have a Y chromosome, then it's impossible for them to carry that trait. So if there's any females that express that trait, we know that it's not Y-linked. Okay, now that's not always the case. If you have a small sample size, for example, and you don't have any females, that doesn't guarantee that it's Y-linked. It just means that it could be, or it could not be. So you need more information. Okay, mitochondrial inheritance is where a trait is passed down from the mother. Okay, that's because the mitochondria comes from the egg of the female. So the only way that you can inherit a mitochondrial trait is if you inherit it from your mother, where your mitochondria came from. So if you look at all of the affected individuals and you look at their mothers, if they have a trait and they express that trait, but their mother does not, then there's no way it's mitochondrial because they have to have gotten it from their mom. So you can cross that one off the list. And again, sample size matters. So if you just have a small sample, and you don't see that pattern, then that doesn't mean that it's necessarily mitochondrial. You just need more information. Once we've gone through and eliminated the easy ones, we can then go through a series of a flow chart that I've included here, starting with figuring out if the trait is a dominant trait or a recessive trait. We can worry about which chromosome it can be found on later. Okay, so the easiest thing to do is to start off by finding two parents that are the same. Either they both express the trait or neither of them do, and find an offspring that is different from the parents. So you could look and see if there are any offspring that do express the trait, but come from parents that neither of them express the trait. If that's the case, then it can't be dominant because that trait had to come from the parents. And if neither of the parents express it, then it can't be dominant. Okay, that means that it has to be recessive. Now, if you don't see that pattern, there's another pattern you can look for, and that's if you have any offspring that do not express the trait, but both of the parents do. Okay, in that case, it can't be recessive. It has to be dominant, because if it was recessive, then the two parents would only carry the recessive traits. That means that the offspring couldn't have anything other than that. Now, if you don't see that, then you just need more information. You need either more family members to survey or a bigger pedigree to find patterns that you could recognize. Now, once you find out if it's dominant or recessive, we're going to look and see if it's autosomal or sex-linked. And that's going to make a difference depending on if it's recessive or not. So looking at my recessive side, if I see that there are two parents that do not express the trait, and they have a daughter that does, then that means that it cannot be sex-linked recessive. It has to be autosomal. And that's because that sex-linked recessive trait would have to come from the mom and the dad. So if the daughter has it, she would have to get one recessive trait from the mom and one recessive trait from the dad. And if the dad only has one X and it's recessive, then he would have to express the trait. So if he doesn't express the trait and the daughter has it, it can't be autosomal. It can't be sex-linked, so it has to be autosomal. Okay, if you don't have a pattern like that, then you just need more information. It could be sex-linked recessive or autosomal recessive. You don't have enough evidence to support one or the other. Now, if it's dominant, and we're trying to determine if it's autosomal or sex-linked, then if you have a father that does express the trait, that means he has the capital or the dominant trait, and he only has one X. So if he has it and it's sex-linked, then that means that every single daughter would have to have it. That's because each daughter gets one from the mom and one from the dad. And the dad only has a dominant one. So no matter what the mom gives, it doesn't matter. If the dad has it, then that's what the daughters are going to express if it's dominant. So if you see a daughter that doesn't have it, but the dad does, then it cannot be sex-linked. It has to be autosomal. So I'm going to go through some examples with this flow chart to help you guys see how to do this. Okay, here's our first example. I can go ahead and cross off Y-linked right from the bat, and that's because of individual number 4. A girl does not have a Y chromosome, so that is impossible. I can also go ahead and cross off mitochondrial, and that's because of individual number 5. Individual 5 expresses a trait, but their mother, number 2, does not. So we know that it didn't come from the mom, so it can't be mitochondrial. Now I'm going to find 2 individuals where the parents are the same and they have offspring that's different. So I'm going to look here at parents 8 and 9 and their child 17. Looking at this, we know that it has to be recessive because we can cross off the dominant ones, because number 17 had to get this trait from their parents. And if the parents carry it, but they don't express it, it must be recessive. It must be hidden by the dominant trait that it's not expressed. Now, looking at my individual number 17, we have a daughter that expresses a recessive trait. So if it's autosomal, it's going to look like this. If it's sex-linked, she would have to have 2 recessive copies of the X chromosome. One which would come from the mom, which could be hidden, and the second which would come from the dad. The dad only has one X chromosome. And because this individual, number 9, does not express the trait, then we can mark off that it's sex-linked, leaving us with it has to be autosomal recessive. Here's another example, and we'll do the same thing. Starting with my Y-linked, I can automatically cross that off because of individuals 2 and 6. I can also go ahead and cross off mitochondrial because of individual 9 and 3. Okay, individual 9 has or does express a trait, and they got it from someone other than their mother. Okay, you can't get a mitochondrial trait from anyone other than your mother. Okay, now let's determine if it's dominant or recessive. Okay, I'm going to find 2 parents that have the same expression and a child that has a different one. So in this case, I'm looking at parents 1 and 2 and their child number 7. Looking at this, I can see that my 2 parents do express the trait and my offspring does not. Okay, looking at this, we know that it can't be recessive because if it was recessive, then both parents would be homozygous recessive, and they could only pass on individuals or gametes that were recessive. The fact that number 7 does not express a trait means that that cannot be the case. So we can mark off this, and we can mark off this. Okay, now let's determine if it's autosomal or sex-linked dominant. So I'm going to look at a father that does express a trait. Like, let's say parent number 4. Parent number 4 would have to have one dominant allele, meaning that the daughter's alleles would come from one from the mom and one from the dad. And if the dad only has one dominant one to pass on, then she would have to express the trait. So because she doesn't, we know that it cannot be sex-linked. Now we're going to do some more practice problems together in class with your teacher so you have an opportunity to ask questions and really go through it on your own.